If a reaction has both the change in entropy and the change in enthalpy with a negative sign, or both the change in entropy and the change in enthalpy with a positive sign, then the reaction will be spontaneous at some temperatures but not at others. And so we can figure out what temperature those are going to be at by using the Gibbs free energy equation. We're going to look at a really simple example. So we're going to look at water going from its liquid state to its gaseous state. You already know the answer to this question. At what temperature is this spontaneous? When does water spontaneously go from a liquid to a gas? Water boils at 100 degrees Celsius at 1 atmosphere pressure, and so you already know that this answer should be about 100 degrees Celsius. Above that temperature, so the range would be 100 degrees Celsius, and above, this is going to be a spontaneous reaction. Below that, it's not spontaneous, but we can actually use this simple example that we already know the answer to in order to calculate it. So we know that the Gibbs free energy is equal to the change in enthalpy minus the temperature times the change in entropy. This question is asking, when is this switching between being spontaneous and non-spontaneous? In order for it to be spontaneous, delta G needs to be negative. In order for it to be non-spontaneous, delta G needs to be positive. But we're asking the question, when does it go from being negative to being positive, or from going positive to negative? And right at that point where it's going between negative and positive, or spontaneous or non-spontaneous, right, in between a negative value and a positive value is 0. So for this instance, we can substitute 0 in for the change in Gibbs, because that's the question we're asking. And then the rest of the equation stays the same. So in order to find this out, you need to pull out your reference sheet or pull out the charts in the back of your book and find delta S and delta H. I have already compiled these just so you know, but in this case, delta H is going to be the standard enthalpy of formation of water in its gaseous state, that's the product, minus the standard enthalpy of formation of water in its liquid state. This is equal to 44 kilojoules per mole. For the entropy, we do the exact same thing. The standard entropy of water as a gas minus the standard entropy of water as a liquid. Oh dear goodness gracious. Okay. Alright, so then you can look those values up in your book or on your reference sheet and you will get 118.8 joules per mole Kelvin. Now those values are standard values, right? That's what this sign means. So standard means these values are actually good at 25 degrees Celsius. But because calculus isn't required, we're going to use those values even though we know we're calculating at a different temperature. But it's going to be an approximation, but it will give us a good idea. As you go on and you learn calculus, and if you continue on in chemistry, you'll learn how to apply that to this situation so you'll get more accurate values. So we said the change in entropy was 118.8 joules per mole Kelvin, and the change in enthalpy is 44 kilojoules per mole. So we can rearrange this equation that we had to solve for temperature. In order to do that, we need to subtract the temperature onto this side is equal to the enthalpy, and then the temperature, which is what we want to know, is going to be equal to the change in enthalpy over the change in the entropy. The only trick here is noticing that these are in different units. So we want to convert one to kilojoules or the other one to joules. It doesn't matter. So if we have 44 kilojoules per mole for the enthalpy, then we have 0.1188 kilojoules per mole Kelvin. The kilojoules cancel, the moles cancel, and we're left with 1 over 1 over Kelvin. If you divide this out, then the temperature is equal to 370.4 Kelvin. We usually deal with things in Celsius, so we can make this into Celsius by subtracting 273.15. This is equal to 97.2 degrees Celsius. Our first question is, does that make sense? We know that the conversion of water from a liquid to a gaseous state happens spontaneously above its at its boiling point, at and above its boiling point, so at 100 degrees Celsius. Like I said, those reference values that we're using are good at 25 degrees Celsius. So this is really close to this. It's not spot on because that change in enthalpy and this entropy values that we're using are only good at 25, and this is at 97 degrees Celsius, good enough. We can say it makes sense because it's awfully close to what we were expecting. I hope that makes sense and cleared up a couple of things. Let me know if you guys have some other questions.